First of all, welcome everybody to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the Biotechnology Center, and I work for the Division of Extension also. And BMM is helping with all the technical stuff, keeping things running so that I'm not the only one pushing the buttons, which is really good. Next week, on February 10th, Mariah Zapara from Penn State will be here, and she'll be talking about a topic near and dear to my heart, which is viruses, but she's going to be talking about viruses of humans and that are as long-lived as the humans. So that's a pretty cool thing, a bit different than some of the ones we've been dealing with. On Monday, February 15th, we're going to have a special Monday night edition of Wednesday Night at the Lab, as is the February 10th talk. The next two talks on February 15th and February 17th are part of UW-Madison's Darwin Days and commemoration of evolution and an exploration of evolution in our lives today. On February 15th, we're going to have a special chance to view, and we'll send out the instructions on how to do this so you can see it really in high quality. The Serengeti Rules, which is one of the documentaries that Sean Carroll, who spoke to us last week, has made, and then he'll come on and we'll do some Q&A and discussion afterwards. And Jaime Cordova is the person here in genetics who's leading that organization, and I appreciate Jaime's work. And then on February 17th, we're gonna have a panel of 4 people from around the country, all talking about the coevolution of mammals and microbes. So that's where we got going the next few presentations. So now I'll start by again welcoming everybody to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension, and on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night by Zoom, 50 times a year. Tonight, it's my pleasure to introduce to you Andrea Strzelek, and I'm going to ask Andrea the 5 questions that I ask everybody. And the first one is, Andrea, where were you born?
I was born actually in Milwaukee, Wisconsin, Old St. Mary's Hospital.
And where'd you go to high school?
I went to Waukesha Catholic Memorial.
And where'd you go to undergrad, and what did you study?
I went to UW-Madison and I studied biochemistry.
Biochem, whoa.
Yep.
And then where'd you go for your master's or PhD?
For both of those, I went to UW-Madison. And so I'm like what I like to call a triple threat badger. And if you don't believe me, my terrace brick says so.
Well, very good. And then you've been to other places since then?
Yeah. Oak Ridge National Lab, the Pacific Northwest National Lab. I was faculty at Texas A&M and Mississippi State until I got the chance to come home to Wisconsin.
And what do you do now? Tell us a little bit about that program.
I run a master's program in engine systems. It's an online master's program for working professionals who are looking to advance in their career. So it's a very specific and dedicated applied program on engines and powertrain. I have also a capstone program in powertrain electrification. So this is very near and dear to my heart. Ooh, we lost your sound, Tom.
Wow, that's because I muted myself. Tonight, you're going to talk with us about the future of hybrid powertrains. And so we're looking forward to hearing your talk. And looks like you're all queued up with sharing your screen. And thanks again for coming tonight and speaking to Wednesday Night at the Lab.
Yeah, thanks for having me. I really appreciate the being here. And I am talking about what I like to think about as our hybrid future. So I want to talk to you about the difference between electric versus electrified powertrains. And there's a distinction there, and I think it's really important that we talk about it. Before we get going, I just like to give you an outline so you know what you're getting into. So I have 5 points here, an objective for the talk. So my objective tonight is to explain the need for and how to comparing apples to apples when it comes to vehicle powertrains. So I'll also start with an introduction. I'll tell you who I am anyway, although I will say Tom's question stole a little bit of my thunder on that. But I also want to tell you from the get-go that I absolutely believe in climate change. I absolutely believe that CO2 is a problem. And because of that, I've dedicated my career to clean engines. And I'll tell you about that. We'll go into some background on how we use energy in transportation and where that energy comes from. We'll give a few engine basics because I can't help myself. And I'll talk about how to evaluate a thermodynamic system. And thermodynamics is the study of energy, its transfers and transformations. And so thermodynamics is the science that governs what we're going to be talking about. And then I want to share some information because I want to challenge some incomplete claims that I've seen in the press. And I have a whole series that I can, share afterward on ways that these claims can be misleading. And when you dig in a little bit more, the true story shows that, the sound bites are not what you need to pay attention to. You need to dig in. And then I'm going to tell you what I think we should do, which is continuously improve all areas. I want to let the engineering and the science dictate our policy because thermodynamics is not political. Okay, so I have to start with a few acknowledgements. I used material from several people and I want to be very upfront about that. Dr. Kelly Senecal from Convergent Science here in Madison, who is really my inspiration for getting the word out and having the chance to have these opportunities to speak on this. He is a Badger, and he gave a TEDx in Madison talk, which kind of is what inspired me to passionately promote this idea. He also started the Hug Your Engine hashtag. So lots of good stuff there. Professor David Foster from the UW-ERC, my PhD advisor and a Badger. Professor Dennis Asanis from the University of Michigan Auto Lab and now president of the University of Delaware. Dr. Graham Conway, who's from Southwest Research, and Dr. Todd Fansler, who worked at GM, but now in his retirement years likes to do some research with us here at UW. So I thank them all for donating material. And I'm really honored to have this opportunity to add my voice to theirs and to give my version of the explanation. So thank you, Tom, and Wednesday Night at the Lab for this opportunity. So what is my objective in being here to talk to you tonight? Well, in this talk, I want to trash some false ideas. I want to tell you that electric vehicles are not zero emission vehicles. And I want to convince you that, in fact, there is absolutely no such thing. When we talk about zero, we're only talking about the tailpipe. And the tailpipe is only part of the story. Electricity has to come from somewhere. And as we were talking about it, before the talk started, in the US, and especially here in Wisconsin, that predominantly comes from coal and fossil fuels. So we have to pay attention to the whole picture, and we'll talk about that. I will also trash the idea that engine technology has been stagnant. It's not. As I like to say all the time, this is not Rudy's diesel. Rudolf Diesel, of course, the inventor of the diesel engine. I think a lot of times when people talk about vehicle technology, they will give the aspirational path of electric vehicles, renewable electricity, and they'll act like, the engine is a dinosaur and has not been changing and evolving. There's things on our side of the table too that give you pathways to clean, green solutions. So what I'm hoping to really trash the idea of is the idea of a silver bullet, or the idea that a green future relies only on a single technology. It doesn't. And my friend Kelly coined the phrase, the future is eclectic. And I think that needs to be true. I think we need to not choose things a priori. We need to let the science and engineering dictate what's the cleanest, most efficient future. And the only way we're going to do that is if we continuously develop in all areas and let the winner emerge rather than choosing it in advance. I also want to show you that what I like to say is dirty is in the details. you know, in order to really evaluate things, you have to draw proper boundaries. And an example of that is this lovely cartoon here, which shows, you know, two vehicles. And the top one is a diesel, and the guy inside who has tailpipe emissions, you know, feels really dirty because, you know, he has visible tailpipe emissions. The guy in the electric vehicle on the bottom has no tailpipe emissions. In fact, most electric vehicles do not even have a tailpipe. And therefore, he's feeling really clean. But the problem is, the reality is that he is using electricity from the power plant there. And so he has distributed emissions, just not at the tailpipe. I also want to show you a little bit about how engines are continuously getting cleaner, including some of the work done right here at UW-Madison in novel combustion strategies and in catalysts. And by the way, this is not only true of electric vehicles, but this cartoon has a version of fuel cells too. Hydrogen does absolutely burn without generating any CO2. When hydrogen burns, you only have water as a product of combustion. However, hydrogen is not naturally occurring as a fuel, and it takes a lot of electricity to get there. Therefore, fuel cell vehicles, while they don't have any CO2 at the tailpipe, do in fact have CO2 emissions associated with them and the formation of that hydrogen. So why am I talking about this in particular? Well, I am a literal engine hugger. And so I am the program director of the Master of Engineering and Engine Systems program here at Wisconsin. And as Tom mentioned, and I mentioned, I am a triple threat badger, studying right here at UW and in the Engine Research Center. I did my PhD work in collaboration with Oak Ridge National Laboratory, and that was sponsored by USDOE, so I like to thank them. Thanks for that PhD. And my work experience after I left Madison, I worked at 2 USDOE labs. There are 17 DOE labs. I've only collected 2. And then I was a professor of mechanical engineering, first at Texas A&M and then at Mississippi State. So I want to say hi to Troy Huron, who I saw join. He was a former student. And then in 2019, I had the opportunity of a lifetime for any Badger. I had the opportunity to come back here to Madison and work at my beloved University of Wisconsin. And so I've been back. So one thing that my students can tell you about me is I am absolutely passionate about thermodynamics. Thermodynamics, as I mentioned before, is the study of energy, its transfers, and its transformations. But in order to do a proper thermodynamic analysis, you really need to set the boundary for that analysis. And I'm going to show you what that means. I also don't believe in the demonization or ban of any technology. Nothing is all good or all bad. There's no such thing as a silver bullet when we look at these technologies. Not one of them is the obvious right answer that will solve all our problems. I also absolutely do believe in engineers, which might be, you know, a hazard of being one. And as I said at the beginning, I believe CO2 emissions are a real problem. I believe they need to be addressed. But I also believe that the fastest way to reduce CO2 is by improving all technologies, including the internal combustion engine, which I'm going to argue is going to be part of our future for at least probably the next 50 years. And so because of the vast infrastructure surrounding that, improvements in the engine and improvements in fuels have the fastest pathway to greening our transportation sector. So let's talk about some background. Here's energy use in the United States. And what you see is that transportation accounts for 34% of all energy used in the United States. And one thing I want to talk about for fuel economy is not only good for your wallet in that green way, it's also green in terms of emissions. Hydrocarbon fuels contain carbon and hydrogen, that's where the name comes from. And when they're burned, the products of combustion are CO2 and water. Therefore, anytime you're able to get more mileage out of a gallon, it means you're also getting more mileage for the same CO2. So therefore, we tend to think of fuel economy and CO2 emissions as kind of being synonymous because they are very much related. Now, in the United States, transportation energy predominantly comes from fossil fuels. You can see my magnifying glass there shows you that 91% of the energy in the transportation sector comes from petroleum. So that's why that's why it's related to the fuel economy, hydrocarbons, that whole 9 yards. So if we take a minute to look at the history of engines, the very first thing I want to point out to you is the first on-vehicle engine was actually a steam engine and not an internal combustion engine at all. So engine development has come quite a long way since the 1760s when we had steam engines on vehicles. The first internal combustion engine wasn't invented until 1807, and the first diesel engine, Rudy's diesel, in 1892. And then that was the first diesel engine that actually ran on coal dust. And the thing that's really important to notice here is, although I don't have a ton of arrows on that timeline, there has been continuous improvement in engines ever since they first appeared. So what is the purpose of an internal combustion engine anyway? Well, the purpose is to produce useful work. And the useful work that we're talking about in this case is rotating shaft power. They do it by using readily available, stable combustion fuels. And that could be liquid fuels like gasoline or diesel, or gas like natural gas, or even propane. These fuels have a high power density, and that's really important for both functionality and speed of the engine. Engines do this efficiently and at low cost. And some cases of the efficiency are greater than 50%. And for those of you that think, well, wait, 50% isn't that great, actually, it really is. There's a lot of factors that come into the case, and we're going to talk about that and how every time you transfer or translate energy, there's potential for losses of it through things like friction or electrical resistance. And so 50% is actually really pretty good. And it's certainly much higher than what we were seeing back in the early days of engines. So there's two types of engines that are most common that we'll talk about a little bit. Spark ignition engines. So those are your gasoline engines. Sorry, looks like someone superseded my sharing there. Gasoline engines, so fuels like gasoline and alcohol. So this is why you see some ethanol in gasoline. And they come in 2-stroke, 4-stroke, and rotary varieties. And then compression ignition engines, so those are your diesel engines, that also come in 2-stroke and 4-stroke varieties. So how does a reciprocating engine produce power? Well, the combustion of fuel releases heat in a closed volume. And so if you remember the ideal gas law from chemistry, that heat released into the volume increases the temperature and pressure. And that increased pressure then pushes on the movable piston, which is connected via the connecting rod. You got to love the engineering nomenclature, to the crankshaft, and it turns and rotates that shaft. So the source energy is the fuel. It's actually the chemical bonds in the fuel. Oxygen from the air provides the oxidizer, and that combustion reaction releases heat. That gas pressure is what pressure is a force exhibited over an area. The area is the top of the piston, and so it forces it down. And in order for this to happen smoothly, you need to coordinate combustion with the piston motion. And we do that by controlling the ignition of the fuel. Now, we can't exceed the physical limits of the engine, so we have boundaries we need to work on for material reasons. So that's the stress, the temperature, the pressure have to stay within a particular realm. Now, this thermodynamic process, combustion is a thermodynamic process, is repeated very quickly over and over on a mechanical cycle. So one of the things I spend a lot of time arguing with people on the internet about is the fact that engines are not thermodynamic cycles. The mechanical cycle has a thermodynamic process in it, but engines do not follow a thermodynamic cycle. And I'll point out to you that the reason is because the closed volume is recharged over and over with new air and fuel. In order for them to be a thermodynamic cycle, you would need to have the same fuel or the same working fluid in it the whole time. And that working fluid couldn't change. By the fact that we bring in fresh air, we bring in fuel, we burn them and create combustion products, means that we are not dealing with the thermodynamic cycle. This is why engines are not limited by Carnot efficiency. And I give a whole nother talk on what the theoretical limit of an internal combustion engine is, but I'll skip that for tonight. The engine control system, the ECU, or the car's computer, as some people like to think about it, is what is used to optimize these processes so that everything is happening. It controls the timing of this. That's why your spark timing is so important, so that it lights off the charge at the right time to create that power. So the 4 strokes of an internal combustion engine, if I give you their, sort of quick and dirty nomenclature of suck, squish, bang, blow, it'll probably help you remember it better than intake, compression, power, and exhaust. So I always like to say that. What happens is the process starts with the intake valve opening. The intake charge comes into the cylinder as the piston is drawn down from top dead center to bottom dead center. So as that piston pulls down that volume, it helps suck that intake charge in. And what the intake charge is different if we're having a gasoline or a diesel engine. So I'll talk about that in a minute. Then when the piston gets to bottom dead center and all that volume is filled with the intake charge, the intake valve closes, and the piston begins its movement up, compressing the gas. So you have both valves closed, so you have a closed volume, and the piston moves up and it squishes and compresses that gas. Then we have the power stroke. So the combustion event happens, and that heat release creates that force that acts on the piston and pushes it down, generating the power. And again, how that power stroke is initiated depends on the kind of engine. So we'll talk about that in a minute. Finally, when the piston is all the way down at bottom dead center after the power stroke, the exhaust valve will open and the piston will head up, pushing the spent gases out of the cylinder. Then the exhaust valve closes and we cycle back to the intake. So cycle, rinse, repeat. So for gasoline engines, which are spark ignited combustion, we have a homogeneous mixture, hopefully, that we are using as our intake charge. What we do is we pre-mix the fuel in the air before it goes into the cylinder, so that hopefully what you have is a nice, very well mixed air fuel mixture that's drawn in and compressed. So we control the load on the engine by throttling that intake by how much we are allowing to go in. The combustion event is initiated by a high energy electrical discharge across the spark plug gap. So that's the spark. And so what you see here is, can you see my pointer? I hope so. The spark initiates the ignition event, and then the flame front, right, burns throughout this mixture. So this golden color here is the unburned region. This little kind of sun corona is the flame front, and you have the burnt products behind it. So the flame moves through, and behind the flame are the burned products. In diesel, it's a different situation. So only air is drawn in as the intake charge in diesel and compressed. The load of the diesel engine is controlled by how much fuel we inject in. Now, because that fuel is injected into a very high temperature, high pressure air, the fuel undergoes an auto ignition process and combusts as it is compression ignited, right, for the combustion. So in diesel, because you're introducing the fuel into that air mixture, you don't have that nice homogeneous mix. you actually end up with a highly heterogeneous mixture in the cylinder. So there's a wide range of mixture concentrations of the fuel in the air where the chemical reactions occur. This is why emissions are a much more significant issue in diesel engines than they are in gasoline. But you know what? That's okay, because people like me work on cleaning that up with after treatment systems. So there are catalytic devices. There's the so-called class of catalytic converters. It's not just one device. For diesel, there are 3 catalytic converters that we use in the system, and it cleans up the exhaust, removing the carbon monoxide, the hydrocarbons, the NOx, and any of the soot. And like I said, you can clean it up with after treatment. I know, I literally wrote the book on it, and you can see it there over my shoulder. So the fuel economy standards, we talked about that fuel economy and CO2 are linked. Fuel economy standards alone are not enough if we want to get a handle on the CO2 situation. So this is the fuel economy standard for 2020, and you see that the US standard for fuel economy for 2020, and you see that it's not meeting our target of where we'd like to be in CO2 level stabilization. But that comes from a lot of reasons. There's an increase in vehicle miles traveled. There's an increase in CO2 emissions from developing nations. And on top of it, the rate of technology penetration on the vehicle fleet is not as fast as we would like. So even if you're coming out with cars every year that get better and better fuel economy and have less and less CO2 emissions, people aren't going out and replacing their cars every 6 months or a year. So it takes a while for the technology to penetrate into the fleet. I also want to take a minute to talk about CAFE, which is the corporate average fuel economy standard. So we have these CAFE standards that are set by class of vehicle. This is why the PT Cruiser is considered to be a light duty truck. When you have, if you're a manufacturer and you have a large range of vehicles that you manufacture, and you want to have a lot of sales in your truck class, right? You want to enable people to buy the trucks that they want to buy. You need your average fuel economy for that class of truck to hit a target. So by making the PT Cruiser fit the definition of a light duty truck, you can average in its relatively higher fuel economy as compared to a quarter-ton pickup truck into that and meet your CAFE standard. So we were talking before the presentation started about metrics that you can game, and I think CAFE fits into that. So when you look at these things that maybe politicians come up with as targets, you have to be really careful on how you set them, because anytime you set up a metric that you can game, it ends up not to be a particularly valuable metric. So one thing I always like to talk about is when did engines become villains anyway? When did engines like start getting all this negative press? And unfortunately, I can point to when, and that's the Dieselgate scandal. If you don't remember what that is, I'll tell you very briefly. I know I could go on and on about this, but Dieselgate affected 11 million model year 2009 to 2015 Volkswagen vehicles that were intentionally programmed. Please note, intentionally programmed not to meet the emission standards. So that means the vehicles absolutely could be cleaned. They just were intentionally programmed not to be. This scandal resulted in some really big fines and jail time for Volkswagen executives. But the result of this was also the beginnings of the claims of the end of internal combustion engines and what I'm going to call the beginning of the EV hype. And I'm going to show you in a minute why I call it hype, because you have to look at the whole system and really make an educated determination on this. So you see here, right, The Economist called the engine roadkill. And what's really special about the picture on the right is that's the BMW headquarters. And the BMW headquarter building was very specifically and famously designed to look like a 4-cylinder engine. And they used lights, right, to change it into looking like batteries with that slogan, "The future is electric." And I think that's what inspired my friend Kelly to make a twist on that and say, no, the future should be eclectic. And hopefully by the end of this, you'll see the reasons why we think so. Okay, so now for some science. It's Wednesday night at the lab, and labs do science. So I'm going to talk a little bit about thermodynamics. Not too much, I promise. When you do a thermodynamic analysis, in order to fairly compare two systems, it's really important that you define them properly. So the system is whatever you want to study. It could be my coffee cup. It could be my cell phone. It could be a car. Whatever we want to study, that's the system. Everything that is not in the system is in the surroundings. And we define the difference between the system and the surroundings by the boundary. So choosing your system and setting the boundary determines where we evaluate energy coming into the system or leaving the system. Same thing with emissions, where they come in or where they leave. And you're going to see in a moment how this is a really important thing to consider when we're talking about these different vehicle powertrains. So are we comparing apples to apples if we only consider tailpipe emissions? So if we only consider CO2 for a moment, and we only consider the vehicles, you see I have a Tesla there. Tesla doesn't have a tailpipe, so there's no tailpipe CO2. And I have a Ford Edge, mostly because that's what I drive. And you see my Ford Edge does have CO2. The issue is it's not proper or fair to do the comparison where you're cherry picking these thermodynamic systems, because take a look at that system on the left. We all live in that same system on the left. And as we continue to fill it up with CO2, we can play all the games we want with the boundaries on the right, but it's not helping our problem with the boundary on the left. So why do I say this is cherry picking to just consider the vehicle? Well, one system is considering the source energy and the other is not. So when we classify these as clean and dirty, it's not a fair comparison because, again, one system is considering the source energy and the other is not. So in order to make a fair comparison, we have to consider the energy source for both cars. So as my students will say, there, I fixed it for you. I put this nice Wisconsin coal power plant into the boundary with the Tesla so that now we're considering all the way from the energy source to its end use. And now what you see is that that's not so clean and this is not so dirty, right? If you consider the energy source from both cars, you have to admit that electricity is not a naturally occurring fuel. We have to make it. And making it can generate CO2 and does if you're in the United States. In the United States, more than 70%, and actually even a little bit north of 75%, comes from coal and other fossil fuels. So you can see this Wired magazine article, and it changes depending upon where you are in the world. If you're in Norway, 98%, and it would be awesome if someone was joining us from Norway or Iceland, where they have 98 and 100% of their electricity coming from renewables. But that's not the situation that we're in right now. And so you have to consider the energy source of the electricity as well. And that's why I've done that in these pictures here on the right, changing the Tesla from being a zero emission vehicle to a distributed emission vehicle. So if we're going to say zero emissions, we need to put a T in there. It needs to be zero tailpipe emissions. Then it becomes a true statement. The other way, it's a little bit misleading. So this energy source argument is not the only place where I feel like there's a little bit of hype when it comes to electric vehicles. And in order to explain that, I need to tell you a little bit more about how you can do analysis of these systems. So someone was asking me a question in the beginning before we started the talk, and this is the part that I was referring to. If we do only a vehicle analysis, the so-called wells to wheels analysis, we're only considering the emissions that are produced during the usage stage of the vehicle. But that's not the full story. So the previous slide with the Tesla and the coal plant and the Ford Edge with its CO2 at the tailpipe, that's wells to wheels. That's looking at just the usage of the vehicle. However, there's also what's called life cycle analysis or cradle to grave. That includes emissions produced by extracting or fabricating the materials that make up the vehicle, including the battery and the motor or the engine. Transporting those materials to the factory, assembly, and all that kind of stuff. And it includes the usage phase. So life cycle analysis is inclusive of vehicle analysis and has more of the whole picture. So wells to wheels emissions is just this first part of my chart here. It covers primary fuel production, fuel refining, fuel distribution, to the fuel station, where you put it into the car and where you use it. One thing that you have to pay attention to is each somewhat handling process of energy can come at a cost. Real processes have losses associated with them. Things like friction, electrical resistance, lost heat to the environment. So this is simplifying it a great deal rather than giving you a whole course on thermodynamics, which I would love to do, but we don't have time for. Every time we handle energy, we lose some of it. So if you look at an engine, we put the energy directly into the system in the form of fuel, where we directly convert it via combustion to power. For a battery electric vehicle, we have more handling steps. First, we have to turn the fuel, often via combustion if you're coal or natural gas, into electricity. Then we're going to transfer the energy via the power lines, where it might meet with some electrical resistance. Then we're going to transfer and chemically store the energy in a battery. So that's another transformation that we're going to have some loss. And then we're going to withdraw the energy from the battery to power the motor. So we're going to unchemically store it. So there's also a potential for loss. And all these things add up. And I want to show you that. The other thing I want to talk about just real quick is talking about how we get energy into the system. And we were talking about this at the beginning a little bit too. When I go to the fuel station, it takes me roughly 2 or 3 minutes to put 15 gallons of gasoline in my car. Gasoline has about 131,000 kilojoules per gallon, which means I transferred nearly 2 megajoules of energy, right? I'm transferring energy at the rate of 16.5 kilowatts. That's super impressive. And if you're not the only car at the gas station, I should put in the picture of the Texas gas station with the 200 pumps. You know, that's a lot of energy that you're transferring very, very quickly there. In comparison, one of the things when you talk about batteries is charging of them takes a lot longer to do that chemical storage of the energy. So if we look at the Tesla 100 kilowatt battery, that's about 360 megajoules, and slow charging of it takes 10 to 14 hours. Rapid charging is 3 to 6 hours, and even fast charging takes more than an hour. Now, you can charge to about 80% charge in 30 minutes in fast charging mode, but this is an unfortunate truth of thermodynamics. The faster you do something, the more it degrades and the more energy you lose. So faster charging ages the battery, and therefore Tesla limits the number of fast charges you can do. So you're not going to drive over the river and through the woods to visit grandma and achieve that by fast charging at stations along the way. Okay, so back to comparing efficiencies on the well to wheel basis. So if you look at just the tank to wheels, and this is what I think people focus on a lot, just the tank to wheels, meaning from the time we put the electricity into the battery electric vehicle, the vehicle is 80% efficient at converting that energy stored in the battery into motive force, right? Your miles per gallon. That's fantastic. Whereas your gasoline vehicle, and this graphic is a little bit dated, but it's such a good one that I like to use it, is more like 32, maybe 35% for gasoline direct injected engines. So that comparison at just tank to wheels looks very, very good for the electric vehicle. And I think this is one of the hype things that I want to warn you about. But when you look at the whole conversion, when you go well to tank and add that to the tank to wheels, you see that actually the power generation from the coal to electricity and transmitting it is only about 30% efficient. Whereas taking the oil from the wellhead through the refinery and transporting it is about 83% efficient. And the truth about efficiencies is they are multiplicative. So 30% times 80% and 83% times 29% ends up with both processes being about 24% efficient. So even on a wells to wheels basis, when you compare the whole story, the efficiencies are actually much more matched than you've probably been led to believe. Now, here's a fun fact about Wisconsin winter, and you in Hawaii, I don't want to hear about it. Right now, it's really cold here. And unfortunately, this is DOE Fact of the Week, by the way, 1164. You can sign up for these DOE Fact of the Week, and they send you a really cool fact every week via email. This was 1164 from a couple weeks ago. And the point of this slide is showing you that fuel economy drops in cold weather, no matter what kind of vehicle you have, but that electric vehicles get a higher penalty on that than gasoline vehicles. So the comparison here is a nice Madison summer day at 77 degrees Fahrenheit, a gasoline vehicle city driving that's set as our 100%. When the weather drops to 20 Fahrenheit, you see that we lose 15% of our fuel economy in that same gasoline vehicle doing the same city driving. If you have a hybrid vehicle, so something like the Volt we were talking about before, or a Prius, you'll start to see more of a 30 to 34% drop. And if you go to a full battery electric, so now the Chevy Bolt or a Tesla, the penalty is more like 39%. So of course, it will vary by vehicle, driving conditions, and many other factors. But on average, this is the impact of weather. So you do have to pay attention to that as part of the entire story of the vehicle efficiency and powertrain. Okay, but that's still not the whole picture, because we also have to talk about manufacturing. And that brings up what we call cradle to grave analysis. So now we're considering the whole picture of my picture there before, from mining the materials and producing the materials, to manufacturing the vehicle, to transporting the vehicle to the car lot where you buy it, to actually then using the vehicle. Cradle to grave also considers that top line as well. So it does also consider the in-use portion. Manufacturing is a big source of CO2. And unfortunately, battery production means that you're already starting with a lot more CO2 in your column at the start before you've even driven the vehicle 1 mile. So let's use this beautiful blue BMW 320d as our comparison vehicle. So it has a diesel engine. It produces about 109 grams per kilometer of CO2 when you're driving it. Manufacturing that engine, making that engine, which is a cast iron block, generates enough CO2 that it's like driving this vehicle 950 miles. So before we've driven this vehicle mile 1, we've already just in manufacturing the engine have made the equivalent CO2 as driving at 950 miles. In comparison, the Nissan Leaf, it is a smaller range battery electric vehicle. So it only has a battery and electric generator motor. It has no engine, but it has a smaller battery because it has a smaller range. So it has a 40 kilowatt hour battery. The amount of CO2 that's generated from the battery production is 4,800 kilograms. That's equivalent of driving that 320d 26,600 miles before you've ever driven that Leaf mile 1. So manufacturing the battery is much more CO2 intensive than manufacturing the engine. When you go to the Tesla Model S, that has a larger range, larger battery. So that's about 12,000 kilograms of CO2 from making that battery. That's the equivalent of driving that 320d 70,000 miles. So before you've even driven that Model S out of your driveway, you have the equivalent of driving the 320d 70,000 miles. So this data comes from Kelly, and it's using 120 kilograms of CO2 per kilowatt hour. That's about the middle of the range. People report wide ranges on that. This is using somewhere in the middle and the average It, of course, depends on where the electricity at the plants are coming from. This is the average for a US mix of power. Okay, so what we just saw is that the bigger the battery, the more the CO2 it takes to create that battery. So that's why there are different starting parts before we've even driven a mile. The smallest was the 320D, right? That engine. Then the smaller range electric vehicle was next. And then finally, the full larger range electric vehicle had the most. What you see is, although the slope of the line for the conventional internal combustion engine vehicle is the steepest, meaning it generates the most CO2 relatively while in use, it still takes about 90,000 miles of driving for the conventional engine to catch up to the amount of CO2 generated from this smaller range electric vehicle, simply because of this starting point. So then the larger range electric vehicle, because it started at such a much higher level, notice that even out here at 180,000 miles driven, we still haven't caught up in terms of total CO2 produced. So that's really important to think about, right? Although you might not be generating CO2 at the tailpipe, and although you might be generating less CO2 by using that electric vehicle, because of your production of the battery, you're still overall generating more CO2. Okay, and now I warned you, don't think this, but maybe you're still thinking, but engines are old technology and batteries are the future. Well, actually, in terms of the percentage of total vehicle sales, electric vehicle sales peaked in 1912. Here's the Waverly Electric, right? At a whopping 2250. We saw actually the first electric vehicles in the 1850s. In the 1890s, there were even taxis that were EVs in New York City. But by the 1920s, they were nearly extinct for many of the same issues that we face today. Battery storage capacity, the so-called range anxiety, how far you can go on a single charge, right? Limited charging stations, that's also infrastructure, right? We see gas stations all over town, but you don't have as many opportunities to charge your electric vehicle. And competition with the internal combustion engine. So note that we're sort of looping back on ourselves in terms of this timeline, and many of the problems that were a problem back in the early electric vehicles are still true today. So even though things are getting better, you have to remember that these problems have been around for a long time. So if you're saying, but batteries are always getting better and we're moving towards renewables for electricity, well, I want to tell you that engines have been improving too, through a variety of different techniques like variable valve actuation, or aggressive exhaust gas recirculation, or high pressure direct fuel injection systems that enabled gasoline direct injection technologies. My personal favorite, particulate filters and lean NOx after treatment. We've been cleaning up and making engines more efficient all along that same development timeline. So one thing I want to caution you of is, if your argument is, but we're moving towards renewables and batteries are getting better, engines are getting better too. And we're also moving towards renewables in terms of fuels. And I'll show you that in a minute. By the way, there's a lot of really great results that we're getting out of continued research into engines. US DOE has several programs. There's the Super Truck program. We're actually now in Super Truck 2. They've nearly doubled the mile per gallon fuel economy of Class 8 trucks. So the semi trucks that are running around delivering all our many Amazon packages, they've nearly demonstrated a doubling of their fuel economy. So research works, right? We can get better in all these areas if we keep working at it. There's also the US DOE Co-Optima program, where they are looking at the evolution of fuels and engines at the same time, right? Building them together to build a cleaner future. And by the way, notice the little graphic down here with miles per gallon. We've been, after we went through a period of, adding a lot of weight to the vehicle for safety and adding a lot of parasitic electronics, some of them which are really nice, like heated seats. You see that we turned a corner and we've been steadily increasing in fuel economy in conventional engine vehicles. Also, just like electricity is getting renewable, fuels are getting sustainable and renewable too. So if you look at things like biofuels, that enables a carbon recycling loop. Instead of releasing the chained hydrocarbons that are in oil, we're now growing plants and removing that CO2 from the air and only re-releasing that same CO2. So biofuels are things that are derived from biomass, plant matter, trees, grasses, agricultural residues, and other biological materials. And there's a range of options. There's things like ethanol, which we already have in vehicles, biodiesel, bioethanol, bioreformate. So things like Virent right here in Madison is working on. There's lots of ways that we're making fuels for internal combustion engines greener and more renewable as well. So as you think about electricity getting more renewable, don't think that we're not on that same path. And in fact, big oil is already working on greening up their refineries. So they're using the existing refinery infrastructure to make these renewable fuels. So this was a slide from Chevron, and you see they are working on greening up the refineries right now. So the advantage to this is we already have a very healthy and well-developed infrastructure for distributing liquid hydrocarbon fuels throughout the US. If we could get to green fuels, which is like saying if we could get to green electricity, well, then we already have this great distribution system for it through the existing pipelines. We already have vehicles that can burn them, and we can get clean that way as well. So there's also these really cool things, net zero carbon e-fuels. This is where what you do is you use abundant renewable electricity. That's where the E comes from. They're electrically driven fuels. And you take waste or CO2 from the air, and you use electricity in a process of a lot of catalytic upgrading to create hydrocarbon fuels from CO2 captured in this process. So this is another CO2 recycle loop that we could be considering for hydrocarbon fuels. So the question is, what should we do to go green? And the answer is the fastest way is to hybridize. There are many levels of electrification when it comes to vehicles. An electrified car is not necessarily electric, but an electric car is electrified. So let's put it this way. A battery electric vehicle is 100% electric. If a car has an exhaust, it's not electric. Electrified means that we're using electric power beyond the basic accessories, and includes all the way up to vehicles using various levels of power beyond that. So you have everything from micro hybrids, which is your start-stop technologies, to full hybrids that are now allowing electric driving, to extended range hybrids where the internal combustion engine is only used to charge the battery. But all of those electrified cases include an internal combustion engine. So when I said at the beginning that I think engines are going to be around for quite a while yet, notice all these electrified cases still use an internal combustion engine. So again, battery electric vehicle is the only one that's fully electric. And I'm going to speed through these slides a little bit quickly, just in the interest of time. Lots of different kinds of hybrids, plug-in hybrids, And there's a lot of advantages to hybridization. You increase fuel efficiency because you're able to downsize the internal combustion engine because the battery makes up for the power. You can run the internal combustion engine at the optimum settings. You can use regenerative braking to recycle previously lost energy that would have been, that can now be restored. And it allows you to shut off the engine at idle, so you're not creating emissions if you're not running anything. There are, like I said already, several levels of electrification and even several arrangements, series and parallel. Both have their advantages and disadvantages. In general, a series hybrid is more efficient but less powerful than a parallel hybrid. So a series hybrid is something like the Chevy Volt that someone mentioned earlier. So here's what a series looks like, where the engine runs the generator. A parallel hybrid means you could run off either one. And then you can have a power split hybrid. This is what your Prius is. But when you look at hybrids and you make a comparison to both of the parents that we had before, so that's that conventional internal combustion engine vehicle, and this is that longer range electric vehicle, note that the hybrid is better than either parent over the entire life cycle of the vehicle. Hybrids do produce a little bit more emissions in the manufacturing phase, but less than full battery electrics because it's a much smaller battery. And making and using a hybrid in the United States produces less CO2 than either a conventional engine or a battery electric car. And you can see that over the life cycle of the engine. So hybrids are electrified, meaning they have both the electric powertrain and the internal combustion engine. So all of these things need to be continuously improving, both the electric side and the internal combustion engine, to further improve here. But what I want to show you is there is a future for engines. They're not going away. So do I think the traditional OEMs, the original equipment manufacturers, are going to be around? Yeah, I do, because I think there is a future for engines for a while. Be careful how you read the headlines. So I stole this slide from Todd Fansler too. This reports of my death have been greatly exaggerated, says the engine in a slight misquoting of Mark Twain. Okay, so wrapping up, because I see I'm down here on time. The future of transportation needs to include diversity. We should not be choosing the winner in advance. Look at the advantages that we saw of the hybrid system that includes both of these things. I think the real key is to be continuously improving in all these areas and let the technology emerge that's going to solve the problem that we want to solve. Let's set targets on CO2 emissions or fuel economy, and let's do honest analysis of the full life cycle of the vehicle in order to make this comparison. There are a lot of technologies that enable efficient powertrains. Things like energy storage, meaning the batteries, clean combustion strategies, fuel cells, alternative fuels, aftertreatment. All these things enable hybrid propulsion options that are going to be cleaner and more efficient than what we've typically seen today. So I'll skip through this quickly, but if you have a conventional vehicle that's using petroleum, you're going to generate the most CO2. As we hybridize, we generate less CO2. As we green up the electrical grid, we see even less CO2. And as we move to biofuels, we reduce the CO2 even further, meaning all of these things contribute to a cleaner future. So what I hope you see here is there is no silver bullet solution. Even though right now it looks like hybrids are the data shows that hybrids are the cleanest, greenest right now, dramatic reduction in fuel consumption and net vehicle emissions can even further improve through efficient energy conversion and next generation biofuels and vehicle electrification and lightweighting of structures. Remember that time of the downslope in the fuel economy? We need to lightweight structures safely, but that will also help with fuel economy. But that has to be guided by a holistic life cycle design and optimization framework that provides an honest comparison of the full life cycle of the powertrain system. The future has to be eclectic. So hopefully, what did we learn in this talk? That there's no such thing as a zero emissions vehicle. It's not zero. We have to draw our system boundary to consider the energy source, because that's where the emissions get generated, is in that conversion of the energy source. We also saw that manufacturing generates emissions, more so for batteries than for engines. So if we want to talk about things like zero emissions vehicle, or my favorite nonsense, partial zero emissions vehicles, we need to put a T in there and admit that we're only talking about the tailpipe. Also, both batteries and engines are old technology. Both of them have been around a long time. Battery and electric vehicles are not new, and both of them are continuously improving and should continuously improve in order to get us to the cleanest, greenest future. And also, we shouldn't pick the winner in advance. We should choose the targets, whether that's efficiency or emissions, and let the engineers go to it. There are so many clever and creative people out there. Thermodynamics is not political. Thermodynamics tells you honestly what the analysis is. So let's not choose a solution based on politics. Let's choose based on science. And we should continue to improve all technologies. You never know what breakthrough might happen, which might jockey that situation. But continuous improvement in all area leads us to a cleaner, greener solution overall. And hopefully right now you see that hybrids are better than either extreme. You get higher efficiency, lower emissions without the range anxiety. And they're really the best near-term solution, or the fastest way to go green. So after all of that, I want to thank you all for your attention and make some acknowledgements. I especially like to point out thank you to my funding sponsors at DOE that helped pay for my education to get me to where I am today. And I'm really honored to have this opportunity to add my voice and give you my version of things. So thank you very much, Wednesday night at the lab.
Thank you very much, Andrea. This has been intriguing. If people would like to ask questions, you have a couple of options. One is you can unmute and ask. The other is you can type in the chat and I will speak the question on your behalf. Does anybody want to start off by unmuting, or should I read one from the chat? Here we go.
I'll jump in, Tom.
Great.
Hi. Not sure where to start, but a couple of factors that I didn't hear about is the lifetime of the vehicle. Anything with a combustion engine just gets dirtier over time. But when we look at its MPG and its CO2 emissions, it's based on, the test done with a brand new car.
No,
but within the same lifetime of anything that's electrified that you're plugging in, like a plug-in or a BEV, is going to get cleaner over time as the grid gets greener.
So I think you're showing your bias there. So number one, let me tell you that electric vehicles, right, because of after treatment, internal combustion engine vehicles, because of after treatment is required to cover the full useful life of the vehicle. So that's not true. They're not getting dirtier. Even if the engine is getting dirtier, the after treatment is there to clean it up. So that part's not true. On top of it, again, you're saying that the energy grid is going to get more renewable, but I just also showed you there's a pathway to more renewable fuels as well. So over the lifetime of the vehicle, any vehicle you bought in 1960 wasn't using ethanol in the gasoline. We're getting more renewable with the fuels. So that vehicle in the 60s running on the gasoline, the ethanol in gasoline now is necessarily cleaner in its emissions than it was running off the straight petroleum fuel in the 60s. So remember that both pathways are getting greener. So I disagree with your analysis. You're falling into that trap of saying electricity is getting greener and fuels are dirty. I showed you.
No, I didn't say fuels are dirty. I said the car gets dirtier, and you're arguing that it doesn't.
It doesn't.
But at the same time, they've done studies where they take a group of cars going down the highway and measure what's coming out of each one of them. And it's like 1 out of 20 cars is actually polluting enough that it didn't even matter that the other 19 were on the highway. And if you look, it's an older car, right?
But okay, so we have a number of ways to deal with that. We have, like, Milwaukee and Waukesha County, that area is a containment zone where they do emissions testing. If we catch it, we know how to fix it with a catalytic after treatment. So that's a fault in there, right? That can be fixed. It doesn't have to get dirtier. 19 of those cars are still as clean as they were on day one because the after treatment is sized to live over the lifetime of the vehicle.
So why aren't we doing that everywhere? Why aren't we doing that in Dane County?
Please call and ask the EPA.
Okay.
I asked a question. When you mentioned the biofuels and the ethanol, you didn't talk about all the fuel that's burned and the CO2 created producing those.
I did, actually. I showed it as part of the refinery. That's part of that refinery pathway when I showed the wells to wheels analysis. I did show that there's CO2 that comes from that.
But
that's part of life cycle analysis. You have to add it all in there.
Andrea, that was fascinating presentation. I learned a lot. Thank you. I'm just a bit puzzled by the announcement that came out with General Motors here, that they are taking a stand that in 2035, I believe it is, all of their vehicles will be electric. I think it was electric, not electrified. I believe it was electric, non-combustion. How do we explain the brains behind, the engineers behind GM to take this stand if this is not what you're showing? I don't understand that.
Well, I'll say a couple things. It probably isn't engineers. GM is run by business people, right? One of the slides I love to show students is who leads each of the major OEMs. GM is, well, now GM is run by Mary Barra, who does have an engineering degree, but I think there are a lot of business decisions that come into play. I don't think it's the engineers that are saying that we should go in this direction. And there's a lot of political pressure. I think the problem is, I've been in rooms where politicians or political aides have said, you know, when you explain to them about thermodynamics and efficiency and you say what's governed by the first law of thermodynamics, they're like, well, we'll look into repealing that. Okay, well, you might as well repeal gravity while you're at it, right? I mean, the problem is a fundamental lack of science education and understanding in relation to these things where people aren't looking at the whole picture. There's a lot of political pressure to go electric. And I think that's a lot of what GM is responding to. I haven't dug into that one as much as others, but I have a whole collection of kind of misleading headlines where it'll say, oh, we're going all electric. And then, you know, when you read into the story, they're really saying they're going electrified. I haven't had a chance to dig into GM more, but I suspect there's a lot of political pressure in that.
I think one of the parts of that announcement was that it was their cars, not all their vehicles. And the problem with the America is we have all these trucks and SUVs. So
I think that's a
really was cars, not all vehicles.
Yeah, that's a really see, that's digging in and reading beyond just the headline, right? So all I just want to say is when you see a headline, headlines are hype, right? Dig in and look at it, and that's one really important further clarification, right? The trucks, the SUVs, and unfortunately, you can make a very, very fuel efficient car. You can make a car that gets, you know, astronomical fuel economy. In fact, the diesel version of the smart car gets something like 72 miles per gallon. The problem is you can't make people buy it. So, you know, we go through this and pushing on fuel economy and a number of things. They can make these, you know, zero tailpipe emission electric cars. But the fact of the matter is if people are buying trucks and SUVs, how does that really help, right? Ford announced about a year ago that they were getting out of the passenger car market and were only going to make crossovers, SUVs, and trucks because that's what their sales are in.
I just looked up the announcement, and what I'm reading here from CNBC is that GM plans to exclusively offer electric vehicles by 2035, ending production of its cars, trucks, and SUVs with diesel and gasoline powered engines. These are aspirations. So it was comprehensive, not just cars. Other
Well,
questions?
Yeah, Andrea, I'd like to ask a question about batteries. Clearly, the biggest problem with CO2 is battery manufacturing or production. Do you see the cost of batteries, or the CO2 cost of batteries coming down, either with totally new battery technologies or just improved manufacturing?
Oh, absolutely. As we green up the electrical grid, the amount of energy that goes into the battery manufacturing, even if that doesn't change, which process improvements always improve efficiency, but as we green up the electrical grid, that will have an impact on batteries. So yes, I absolutely see that decreasing. But that CO2 production is only one of the issues with batteries. Amnesty International, for example, has identified cobalt mining that you need for making these batteries as one of the biggest violations of human rights, right? Unfortunately, cobalt mines tend to be mined by child slave labor in the Democratic Republic of Congo. So you can read all kinds of articles on that. Mining, so yes, the production of batteries will change, but mining of the battery materials, right? Those are still really CO2 intensive processes. So yes, it will absolutely get better. Every single thing we've talked about here, every single metric, whether we're talking about internal combustion engines or battery electric vehicles, is going to get better. It's just the rate at which they get better and where they, asymptotically level off at that is unknown right now. We can't possibly know what people will come up with in the future, which is why I'm just saying we need to keep developing in all ways to get to that cleanest technology.
Sandy Rotter asked in the chat, wonder if you've done anticipatory life cycle assessment, and will there be a change to a circular or shared automobile economy?
Yeah, so there was a presentation that I saw by GM a couple years ago where they talked about the idea that we would go away from owning personal vehicles, and that between autonomous vehicles and ride sharing, car sharing, we would get into a situation where people probably wouldn't own their own vehicle, they would just own a share in a vehicle. That's all possible. I will say it would cause the need for massive shifts in the way we currently do business. If we didn't all have our own vehicles, we couldn't all be driving to work at the same time, right? We would need to kind of stage all that kind of stuff. 2 years ago, pre-COVID, I couldn't imagine something causing a massive shift in the way we work. Now, where a lot of us are working from home and barely commuting, I think we see, we've already seen massive changes, right? So, yeah, there's been all kinds of different analyses done on that. I haven't done it personally, but you can find in the literature a number of studies that includes things like ride sharing, as well as just looking at greening up the grid or greening up fuels.
And then why don't I go back and forth between chat and spoken question. We just did a chat, so if there's somebody who'd like to ask
I have a question. Yeah, you're an expert on cleaning up exhaust, and I know for a fact that California has placed about 15 NOx sensors on their highways to pick up people, truck companies and drivers who disable their ammonia and urea based systems for taking the NOx out.
Yeah.
And this is a serious problem. A lot of truck owners drive their vehicles for a million miles, and they also don't like the fact that these cleaning up cleaning systems seem to decrease mileage by, the estimate I've seen is about 10%.
Oh,
So
no, that's old data. Yes, when these things were first new, they did represent a 10% fuel penalty. These days, it's more around 1%. But yes, they don't even want to lose 1%, right?
yeah, so you know, how do we fix that? I mean, California wants to. They've got an NOx sniffing system based on spectrometry. They can instantly pick up the diluted fumes from a truck and take a picture of the license plate, and then they're going to try to find people into repairing their truck and keeping it clean. I assume these offenders are heavily polluting compared to people who run an honest business.
Yeah, and so I definitely think enforcement is part of the overall solution, right? I mean, NOx is colorless, right? So you can't see it as easily. You can use some IR cameras, so you could equip law enforcement with IR cameras who could then see who was polluting and pull them over right away and give them a ticket. But the system that you've described is what's called remote sensing with portable emissions monitoring systems. And yes, it's a way, you know, the question before, why aren't we doing emissions measurements in Dane County or things like that? This kind of enforcement is in fact possible. We could be doing it. We could be doing it everywhere to enforce people to use the devices that people like me work on very hard and clean up. One of the things I've always been confused about, though, is just the lack of desire to enforce. So when I lived in Texas, it was very common for people to punch their particulate filter so that they could roll coal, right? So that was where you'd be at a stoplight and then someone in a diesel truck would step on the gas and you'd get the big black plume. And besides wanting to cry because, you know, my PhD work was on diesel particulate filters and that hurt my feelings, it also made me want to cry from just the amount of pollution they were putting out. On the books in Texas, the law is that you could be fined up to $15,000 for defeating your emissions control device. Soot is visible. Why aren't they enforcing that? Why aren't they giving people tickets? Why aren't they? It becomes a local government control issue, right? And so, yes, California is definitely the most aggressive in terms of these things, but there's a number of places that do this kind of remote sensing and ticketing, and enforcement is one tool we have to getting to cleaner air, right?
Now we'll do a chat one. I think you addressed Genevieve Murtaugh's question about about all the fuel to grow corn and to refine it. So I'd like to ask James Bennis's question. How about compressed natural gas? And I'd like to add to that, what about hydrogen fuel?
Yeah, so hydrogen fuel is what goes into fuel cells, right? That's the same sort of problem as the batteries. It takes a lot of energy to generate the hydrogen. So you're sort of in the same situation. You can burn hydrogen in an internal combustion engine. You don't have to only burn it in a fuel cell. You can burn it in an engine. Diesel engines can burn hydrogen. The problem, again, it becomes the creation of the hydrogen, just like electricity. It's in that same boat. With compressed natural gas, that's a great option. It's a great option. There's a process called reaction controlled compression ignition or dual fuel combustion that was really heavily promoted by Professor Rolf Reitz at UW here. And they showed amazing levels of efficiency that you could get if you used compressed natural gas with a little bit of diesel fuel. You could get really great efficiencies and all that. The challenge with natural gas, and something that we're hopefully going to be working on here at UW, is methane slip emissions. So methane has a higher global warming potential than CO2. And so if some of that methane makes it back out of the engine, either because it didn't burn or because of leaks in filling or things like that, it can have a really, really big impact on because of its global warming potential. And right now we don't have very efficient catalysts to deal with methane emissions. And so that's an area of active research that we're working on. But the compressed natural gas is a much lower carbon fuel, and therefore would have resultingly lower CO2 emissions.
And now, thank you. And now a spoken question, if anybody's got one.
I was hoping to hear about whether or not carbon capture of some sort might be better on fuel, on the smokestacks of the generating plant versus the coming out the tailpipes. What are the comparisons? Because you're talking about CO2 production, but is it possible when the electricity is generated through a power plant that they are able to capture that CO2 and reduce the count that you're quoting? And this would also apply, for example, to a battery factory. Would they be able to do the same thing?
Sure. So the battery factory, a lot of the battery manufacture comes from the energy intensity of the process. So it's really back to the power plant. Theoretically,
Okay.
yes, carbon capture would be easier at a stationary source where you could put some sort of device in there. The truth of the matter is we don't have mature carbon capture technologies, right? The most mature carbon capture technologies we have is trees and plants. So, but we don't have mature ways of doing it effectively to reduce CO2 by that. Again, that's an area we should continue actively researching, right? People have looked at having algae farms next to coal plants, right? So that you could run the CO2 through there and hopefully get the algae to eat it and capture it. None of that has matured yet to a place where we could use it. So right now, the answer is no. But again, something that we should be continually looking at. And that's kind of one of the thoughts behind this e-fuel idea is, could you take something that's creating a lot of CO2, could you capture that CO2 and recycle it, right, by taking it and upgrading it back into fuel so that you can use it again in the process.
Thank you very much. You have terrific energy.
No.
Thank you.
Well, coffee.
We have a chat question. What is the leading biofuel being researched that could come to market first across the USA? And I'm assuming that's beyond ethanol.
Well, so I would say the leading biofuel is ethanol, which is already out there. Biodiesel would fit in number 2. It's already out there. It's blended in diesel up to 5%. You got to be a little careful with biodiesel, though. That same Wisconsin winter that kills your efficiency biodiesel has a pretty high cloud point. When I was working at Oak Ridge National Lab and I went out to go get some biodiesel from one of the drums outside on a cold Tennessee winter day, it had actually solidified in the drum. So you have to be careful in climates like Wisconsin and Minnesota that you're not blending too much in there and creating some Crisco in your fuel tank. But those are already out there and running. Then, and here's another political thing for you. When you take soy oil or corn oil and you do this process called transesterification, you make it into an ester molecule, which can be used as a fuel. That's called biodiesel. When you take that same soy oil or corn oil and you send it to the refinery and they hydrotreat it and process it and make it something that looks like a fuel, that's called renewable diesel. And so there's a big, the ag lobby, right, has very successfully lobbied that renewable diesel, or sometimes called green diesel, doesn't get the same tax advantages as biodiesel. And so this becomes another kind of question of, well, wait, if the goal is to green up our fuels, why are we doing things that disincentivize a fast way of doing it at the refinery? I don't have an answer for you there.
Very good. Now to a spoken question, if anyone has one. Go to a chat question then. Walt Shalick's daughter says, hi, I really enjoyed your lecture. I'm 14 and I was just wondering what your recommendation for a first car would be.
Oh, I have a lot of thoughts on that. So and when I was 14, I'll tell you, I embarked on a demonstration of responsibility by washing all the family cars and waxing all the family cars because I had this same kind of question. It didn't work, so no. Anyway, I would say that there's actually a lot of really inexpensive hybrid models. If you go to hugyourengine.com, my friend Kelly wrote a really great story about taking his two sons around car lots in Madison and looking at inexpensive, high efficiency vehicles. There's a number of models out there on the market that are, way, way less expensive than a Tesla, and that get very, very good fuel economy, have low emissions. So I'll point you to that as a good resource, but also fueleconomy.gov, which is an Oak Ridge National Lab maintained website, is a great place to look in terms of if fuel economy, and we just said fuel economy is related to CO2. That's a great place to look for resources on how to decide, between vehicles.
That was a chat question, so if somebody would like to ask a question aloud, that would be great. If not, the next chat question is, what about battery disposal issues? And next person wrote, batteries should be recycled, not disposed of. But if you want to touch on
I agree.
batteries.
Yeah, and especially as our demand for lithium grows short, I think there's a lot of, actually, interestingly enough, a lot of the companies that make automotive catalysts, like Umicore is one in Michigan. They also have battery recycling plants because they know how to deal with all the metals involved and all that kind of stuff. So yes, I definitely agree. Batteries should be recycled. One idea that's been talked about a lot is battery swapping. Instead of you go someplace and charge your battery, what if you could pull into a fuel station, swap out your depleted battery for a new battery, and then drive off? That would be one way to deal with the infrastructure needs. That would also cause us to probably converge on kind of a single battery technology and maybe set us up for something that would be set for recycling. But now you need all the manufacturers to agree on a battery and all these kinds of things and set up that infrastructure. So there's a lot of good ideas for how we could do that, how we could increase battery recycling, but we're not there yet.
All right. Any other spoken questions?
Well, that goes to my question of the circular economy that addresses all those questions about reuse of the parts, and the EU is way ahead of the United States.
Yeah, I mean, absolutely, right? I mean, there's a number of things that we have to look at in terms of recycling and reuse.
And then let's see. I just lost that one. Michael Green asks, on the production side, realistically, how much progress do you foresee in reducing the fossil fuel carbon footprint of manufacturing?
Oh, that's hard to really guess, right? I mean, a lot of the manufacturing is also tied to grid power, so it's hard to guess how that would impact. I think the ideal dream team to address this question, right, might be people from the national academies of scientists and engineers with a economist, with a sociologist, right? So that we can consider the full picture on this. What we really need is a group, right? An engine engineer, a electric motor engineer, an economist, a sociologist. You need all these people kind of working together to do the complete analysis. I've talked about life cycle analysis from an energy standpoint, but that's really only part of the picture, right? And I'm just not experienced enough in manufacturing to answer that.
If there are no other spoken questions, I want to circle back to something that Larry Winkler typed in during your talk. He said, as I understand it, doubling the speed requires 4 times the energy. How does that translate into fuel use? Would doing things more slowly improve things?
Yeah, actually, Larry, you are right on with that. I talk about this a lot when I teach thermodynamics. The faster you do a process, the more degradation that occurs. That's part of the second law of energy. It's an unfortunate truth. But at some point, you got to weigh these factors, right? If I told you, if you wanted to drive to Chicago and I said, okay, Larry, I have 2 options for you. I have one that's, 40% efficient and I have one that's 99% efficient. Which do you choose? The next question you have to ask me is, how long do they each take? Because it's true, the slower we do things, there's trade-offs on this, but the slower we do things, the less, kind of energy we lose to entropy. But, if it's going to take you 99 years to get to Chicago and the 99% efficient way, then it's less attractive if the 40% efficient way can get you there in an hour and a half, right? So it's all on trade-offs. But this is one of the thought processes surrounding speed limits, right? At a 55-mile-an-hour speed limit, you get better fuel economy than you do at 75 mile per hour. So that's a lot that goes into setting speed limits nationwide, or at least within the state, right? Is looking at things like fuel economy.
Any other questions? Not seen any in, let's see. Michael Green asks, in their new announcement, what do you think Google and Ford are planning? Was it, and then there was another one with Apple and
I don't know, but I think that has a lot more to do with vehicle autonomy. I can't say for sure, but personally, as someone who really likes vehicles, I'm just thinking, would I want an autonomous Ferrari? No, because the fun is in driving it. I do think there are a lot of great uses for autonomous vehicles, especially for children or elderly or disabled people who can't drive on their own. I think there's a great potential for that. But I suspect that Google, Ford, or any of the Apple announcements have a lot more to do with autonomy than they do with efficiency but those, don't forget, that's going to add another parasitic electric load, right? If you're running all these sensors and LiDAR and radar and computers to, determine all this stuff, you're also adding a lot of electric demand to the vehicle. And so I referred to them as parasitic electronics, but everything that you do that takes power, that, like heated seats or, the infotainment systems or all that kind of stuff, that power has to come from somewhere. And it comes from the engine in a conventional vehicle. And every bit of power that you take to run all those electronics is taking away from your fuel economy. So, there's trade-offs in that as well.
So we've talked about 4-wheel and bigger vehicles. I'm going to throw a little curveball in here at the end. What's your assessment of electrified bicycles and electrified motorbikes or hybrids thereof?
Yeah, again, I think hybridization always makes sense. It makes sense from the standpoint of it allows both technologies to run in their sweet spots, right? They actually pair together really well. And so then you can run them both in their most efficient kind of ways, which is where you lead to the overall better efficiency for the hybrid case. Personally, in terms of bicycles, the reason I ride my bike is to get exercise. So electrifying my bike is not going to help with that. So that's not something I would be interested in. But again, I understand that people like them, and it's a personal choice.
Are there hybrid motorcycles? I've seen that Harley Davidson's working on an all electric. I'm wondering if there are hybrids in the frame.
I haven't seen anything in hybrid. Yes, I know Harley has an all electric one. I haven't seen anything in hybrids. But you know, one of the other things that would be really interesting to see is like a diesel electric hybrid. There's a couple issues with that though. Those are the two most expensive powertrains. And so then you'd have both really expensive powertrains on there. They would be the most efficient. BMW made a hybrid X5 that got like 62 miles per gallon. It was brilliant diesel hybrid. And I think it's also an opportunity in terms of heavy duty trucks. But I think the big concern when you go to the class 8 vehicles, so the semi trucks that move around our freight and Amazon packages, is that the battery adds weight and volume. And so that means you're trading off less freight that you can carry. And so when you look at like fully electric trucks, like they talk about, there's a lot of weight that comes from the battery. And that's another thing we didn't talk about. As the vehicle gets heavier, you may not see particulate emissions from the propulsion source, but you're going to start seeing them in increased tire wear, right? And so what we see is a lot more particulates generated from the tires of electric vehicles because they're heavier than conventional vehicles. But for heavy duty vehicles, right, that weight and that volume that the battery takes up means less packages that they can carry in there. And that goes to the economics of running a freight line and everything. So again, nothing is just that simple of an answer, right? There's all kinds of things that come into play.
Very good. Well, thank you very much again. This has been fantastic conversation.
Yeah, it's been really fun.
Especially when I tuned in. It was like, wow, they're in the Q&A already. So it's great to have it before, great to have it afterwards. And thank you again for the splendid presentation. Hope to see everybody next week for the presentation on human viruses that are as long-lived as their human hosts. And appreciate it, everybody. Talk to you soon.
All right, bye.
Bye.